Good morning everyone. Welcome to the third and last lecture for this particular week, where we are talking about the gas vapor mixtures and its application to different kind of psychrometric processes. Now over previous two lectures, you have been introduced to different kind of parameters or properties that we commonly associated with the gas vapor mixtures. Then in the second lecture, we have discussed about the psychrometric chart and its application in the field of air conditioning to be particular. And also we have talked about different kind of psychrometric processes like the sensible heating and cooling processes, humidification and dehumidification processes, and also processes like heating and humidification or cooling and dehumidifications, etc. So, these are very common processes that we commonly encountered in air conditioning devices, and therefore, it is important to have some idea about each of them. But as we have seen, the thermodynamic analysis for such systems or such psychrometric processes are not difficult. We just have to plot the processes on the psychrometric chart for the representation purpose, and then using simple mass balance and energy balance, we can get all the required thermodynamic parameters. And it is also important to note that the mass balance commonly needs to be performed on both the dry air part and the water vapor part separately, because both of them can change individually. Like the examples that we have discussed in the previous lecture, there we were just modulating with the water vapor part. Like during the humidification or dehumidification process, it is the water vapor quantity that changes accordingly the specific humidity or maybe relative humidity or maybe both that keeps on changing, particularly the specific humidity I should say. Whereas during the sensible heating or cooling processes, the specific humidity remains constant, where relative humidity may change depending on the direction of change in temperature. Similarly, the processes where we have simultaneous modulation of temperature and humidity, we also have changes in the water vapor content. But in none of the processes there is any change in the dry air quantity, and therefore, quite often for analyzing these processes, we just do not bother about the dry air part, simply because there is no change. We do not have to write any mass conservation equation for the dry air part, we just have to consider the mass conservation for the water vapor part. Again, as a quick recap, here again I am having a psychrometric chart where various psychrometric processes are shown. Here the horizontal axis instead of small t, let us use capital T, which is commonly given in Celsius, degree Celsius, that is the convention that we are following so far. So, starting from this particular point shown by the circle, there are 8 different processes shown here. Let us try to identify the nature of each of the processes. So, if that point is O, then OA, what kind of process is this? Can you say? During the process, the temperature is increasing, specific humidity remains constant. Therefore, this process is a sensible heating process. During the sensible heating process, what is happening to the concerned parameters? Your temperature is increasing, specific humidity remains constant. What about relative humidity? What will happen to the relative humidity? We know that as the temperature is increasing, the saturation pressure corresponding to the temperature, that also increases, and therefore, the denominator term in the definition of the relative humidity, that keeps on becoming larger while the numerator remains the same, and therefore, phi decreases. You can also get that idea from the psychrometric chart, because this line is the saturation curve corresponding to the 100% relative humidity, and as we are moving inwards, then we are having different relative humidity lines, but the relative humidity is continuously decreasing as we are going forward, that is relative humidity increases in this particular direction. So, as we are moving from point O to A, we are actually having a decrease in the relative humidity. Similarly, O to B, this process during which temperature decreases and omega remains the same. So, it is a sensible cooling process during which the temperature decreases, again omega remains the same, and relative humidity, what will happen to that? Now, we are moving towards the saturation curve, so relative humidity will increase. Process O to C, what kind of process is this? Temperature is constant, specific humidity is increasing. So, this is a humidification process. During this process, the moisture content is changing, but temperature is not changing. So, during this process, the temperature remains constant, omega is increasing. What will happen to phi? What will happen to the relative humidity? As temperature is constant, so like in the definition of phi, we know that we have partial pressure for water vapor divided by the partial pressure, the saturation pressure corresponding to the temperature. As temperature is constant, the saturation pressure is also constant. So, the numerator, while the numerator changes, the denominator remains constant. Now, during this humidification process, as omega is increasing, means the moisture content in the sample is increasing, accordingly the numerator is increasing. So, phi is also going to increase because the denominator remains constant. And the reverse process of this one, O2D, during which the moisture content decreases, but temperature remains constant. So, it is a dehumidification process, during which again the temperature remains constant, omega is decreasing, and what will happen to phi? As moisture content is decreasing, the partial pressure for the water vapor part will also decrease, denominator remains same, accordingly phi will also decrease. Now, let us pick up O to E. What is happening during this process? Both temperature and omega are increasing. So, we should call this one a heating and humidification process. In the previous lecture, we have seen this particular process and also solved one numerical problem on this. So, during this process temperature increases, omega also increases. What about phi? Now, it is difficult to say actually from this diagram, because it is very much possible that depending upon the combination of this temperature and omega, phi may increase, phi may decrease, or phi may remains the same as well. So, we are not sure about the value of this phi, because during this process if you look at the expression for this phi, omega is increasing. So, the partial pressure for water vapor is increasing, but as the temperature is increasing, the saturation pressure is also increasing. So, both numerator and denominator are increasing. So, we are not sure about the change in phi. Similarly, if we look at OF, then what is happening during this process? Temperature is decreasing, moisture content is also decreasing. So, this is the cooling and dehumidification process. While the heating and humidification is the most common kind of process performed in colder areas, cold and dry areas, cooling and dehumidification is the most common kind of process that you will encounter in warm and wet or warm and humid areas. So, during this process, just opposite to the previous one, temperature decreases, omega decreases, and again we are not sure about the changes in phi, because in the expression for the relative humidity, both the numerator and denominator are decreasing. So, the magnitude of phi can change in any direction. Now, you have process O to H, or sorry, O to G first. What is happening during this one? Temperature is decreasing, omega is increasing. So, temperature is decreasing means it is cooling, but it is humidification. It is cooling and humidification, means during this process temperature is decreasing, but omega is increasing. What will happen to phi? We can we say from the chart, here this point G is moving towards the saturation curve. So, phi should increase, and from the mathematical expression, here the moisture content is increasing. So, the partial pressure for water vapor, that is in the numerator, that will increase, and saturation pressure, as the temperature is decreasing, the saturation pressure will decrease. So, we are having the numerator increasing, denominator is decreasing. So, phi has to increase in both count. Similarly, the last one O to H, during which the temperature is increasing. So, we are having heating, but moisture content is decreasing. So, heating and dehumidification. The last two processes may not be the most common one, but cold and humidification you can find, because during the dry areas where during winter during the dry areas, during summer we may have to go for simultaneous cooling and humidification. Heating and dehumidification is much less common, may be required in certain industrial processes, but not very common in domestic air conditioning. So, during this process, as you can see from the chart, temperature is increasing, omega is decreasing. What will happen to phi? So, phi, we are moving further away from the saturation curve. So, phi also has to decrease. Again, from the mathematical expression point of view, both the numerator and denominator, here the numerator is decreasing because omega is decreasing, denominator is increasing. So, in both count phi has to decrease. Now, the most common information that are generally provided by the weather department are temperature, that is the dry bulb temperature you can say, and the relative humidity, which is nothing but the phi, and of course, pressure we are assuming as the atmospheric pressure. So, we can easily identify this point on a psychrometric chart and identify the magnitudes of other relevant quantities, or we can go by the mathematical relations that we have developed in the previous lecture or in the first lecture, truly speaking. If you know the dry bulb temperature and specific humidity or relative humidity rather, how can you calculate the specific humidity from there? How can you calculate omega from this? You know that omega and phi has a relation something like 0.622 into phi times the saturation pressure corresponding to the given temperature, that is I should write the dry bulb temperature, and divided by pressure minus the saturation pressure times the relative humidity. So, we can get omega from there, and once you get omega from this, we know how to calculate enthalpy. Enthalpy will become Cp for dry air into the dry bulb temperature, this is for the dry air part, plus omega into, it will be the, we know the magnitude 2500.9 plus 1.82 T dry bulb, this is for the moisture part. So, instead of writing this, so you can directly replace the Cp for dry air, which is 1.005. So, we can get the enthalpy using the omega and dry bulb temperature. We can also calculate the wet bulb temperature the same way, and if the wet bulb temperature is given, like if you are not very common, but in certain industrial processes, particularly if you are having a wet bulb thermometer which is giving you the values of both dry bulb and wet bulb temperature, then instead of phi you know the value of T wet bulb temperature and T dry bulb temperature. So, from there how can you calculate omega? Remember the mathematical analysis that we have performed corresponding to the adiabatic saturator, there omega was obtained the Cp for dry air part 0.005 into T for dry bulb minus T for wet bulb plus omega s into HFG corresponding to this wet bulb temperature, and divided by Hg corresponding to the dry bulb temperature minus Hf corresponding to the wet bulb temperature. Here this omega s corresponds to the specific humidity corresponding to the wet bulb temperature point, which is nothing but 0.622 into the saturation pressure corresponding to the wet bulb temperature by P minus P saturation corresponding to the wet bulb temperature. So, this way by from the knowledge of this dry bulb and wet bulb temperature you can get the omega, and then successively you can get enthalpy, specific volume, etc., or if you know the dry bulb temperature and phi, we can go for the same analysis. Now, I would like to talk about another psychrometric process, like 8 of the processes we have listed here, and you know how to analyze each of them. But there is another one, all the 8 that we are seeing here, there we are not having any change in the dry bulb, the dry air component, but there may or may not be change in the water vapor part, but it is always compulsory that the dry air part remains the same. But that is not the case in this particular situation. Here we are talking about an adiabatic mixing. We are having two different streams of air coming in with different properties, like the stream 1 is having specific humidity of omega 1 and enthalpy of H 1, stream 2 is having specific humidity of omega 2 and enthalpy of H 2, and they are mixing with each other in this adiabatic chamber, and finally coming out with omega 3 and H 3. Their mass flow rates are also different. Let us say the mass flow rate for this one, at least the dry air part is 1, this is corresponding mass flow rate for dry air part is 2, and this final mass flow rate for the dry air part is 3 in this case. This is a representation on the corresponding psychrometric chart. I am coming there, but before that let us just perform the mass balance on this. For the here the dry air quantity is changing, so we have to perform the mass balance on the dry air as well. So, we can easily write m dot dry air 1 plus m dot dry air 2 is equal to m dot dry air 3, So, we are having the mass of the final mixture, the dry air component. Now, if you write the for the water vapor part, m dot water vapor for part 1 plus m dot water vapor for part 2 should be equal to m dot water vapor for part 3, assuming there is no condensation happening or no additional moisture being added to the mixture. Then from there we can write for the first part, it can be written as omega 1 into m dot dry air for 1 plus omega 2 into m dot dry air for 2 is equal to omega 3 into m dot dry air for 3. From here we can get the specific humidity for the final mixture to be equal to omega 1 into m dot dry air for 1 plus omega 2 into m dot dry air for 2 by m dot 3 dry air for 3, that is m dot dry air for 1 plus m dot dry air for 2. This is the final the specific humidity for the final mixture. Similarly, if we perform an energy balance on the same, then for the mixture or for the stream 1, we can write the total energy content for this one will be m dot dry air 1 into H 1 plus for the stream 2 m dot dry air 2 into H 2, and that is coming out with m dot dry air 3 into H 3. From where we can write the enthalpy for the final mixture to be equal to m dot dry air 1 H 1 plus m dot dry air 2 H 2 by m dot dry air 1 plus m dot dry air 2. So, if we know the mass flow rate for the dry air part and also the properties for both the streams, we can also get the properties for the final stream. Now, if we just compare this these expressions that we have just developed from this one and also from this one, actually there is something very interesting that we can develop, that is if we write m dot dry air for 1 divided by m dot dry air for 2, then you will find it will be coming as omega 2 minus omega 3 by omega 3 minus omega 1, and from the energy balance it can be written as H 2 minus H 3 by H 3 minus H 1. This is just simple manipulation of the two expressions that we have just developed. From there we can easily obtain this particular expression. So, from the mass balance expression that we have got, just separate out m dot dry air part and similarly m dot dry air part for 1 and m dot dry air part for 2. So, from there you will be able to get this one, and same from the energy balance you will be getting the expression in terms of enthalpy. So, what does that shows? Look at the graph that we have here. So, this point 1 is the state for stream 1, point 2 refers to the state for the stream 2. There are temperature T 1 or corresponding enthalpy for stream 1 is H 1, specific humidity is omega 1, similarly for stream 2 it is H 2 and omega 2. Now, during this mixing process, of course, the final point 3 will be lying somewhere along the straight line joining point 1 and 2, but where that straight line will be? For that we can easily identify this particular magnitude of H 3 and omega 3, because the ratio of the mass flow rate for these two streams will determine the position of this omega 3 and H 3. Now, as this ratio is always given by this omega 2 minus omega 3 upon omega 3 minus omega 1, therefore, the distance between this, that is omega 2 minus omega 1, actually is getting divided into two parts. We can write this one as omega 2 minus omega 3 minus omega 3 minus omega 1, and this is the first part omega 2 minus omega 3, this is the second part omega 3 minus omega 1. Now, depending on the ratio of the mass flow rates for this stream, there is only one possible value of omega 3, and therefore, the final point 3 should lie along this particular dotted line corresponding to this omega 3. But the enthalpy ratio also has to be maintained, and therefore, whatever the dotted line that we are getting corresponding to H 3, this point 3 should also lie on that particular line. That means, the only position the 3 can have is the intersection of these two dotted lines, the one corresponding to omega 3 and the one corresponding to H 3, it will lie in the intersection of that. Only by balancing the mass flow rates for these two quantities or the ratio of the mass flow rates for the dry air part, we can change the position of 3. Such kind of adiabatic mixing is very common in air conditioning application. Like in common air conditioners, you will find there are 2 fans. In one, the fresh air which has just been conditioned inside the air conditioner is supplied to the room, whereas using the other fan, which is a suction fan, the used air from the room is picked up. It is being dragged back and it goes to the outside surrounding. But if we in every cycle we are just trying to remove entire quantity of air and again fill that particular gap by a fresh supply of conditioned air, then the load on the fans will be too high and also the load on the air conditioners will be too high. So, quite often we just do not discard the entire quantity of the exhaust, rather a part of the exhaust comes back and gets mixed with the freshly condensed air, thereby reducing the quantity of condensed fresh conditioned air requirement. And it is very much possible, like suppose if we are taking say 100 units of air back from the room via the exhaust, maybe only 30 unit of that goes to the surrounding, remaining 70 unit comes in and that gets mixed with 30 units of fresh conditioned air, and subsequently the entire 100 unit of this mixture comes back to the room. So, if we are rejecting or exhausting this entire 100 units of air, then your air conditioner has to condition again 100 units of air. But in this situation, because of the mixing, we just have to condition only 30 units of this. Of course, this fraction like the 70-30 that I have mentioned, that depends upon what kind of applications you are in. This 30 or 40% is very common ratios that we get in domestic air conditioners, whereas in critical applications like say in a hospital, there probably 100% fresh air is supplied. Now, let us try to solve one quick example to see this mixing process. Here there are 2 streams. So, for the stream 1, volume flow rate is given as 30 meter cube per minute. Okay. So, T dry bulb 1 is equal to 15 degree Celsius, T wet bulb 1 is equal to 13 degree Celsius. For the second stream, the volume flow rate is given as 12 meter cube per minute. The dry bulb temperature corresponding to this 2 is given as 25 degree Celsius, wet bulb temperature corresponding to 2 is given as 18 degree Celsius. We have to determine the dry bulb and wet bulb temperature of the resultant mixture. Now, we know the dry bulb and wet bulb temperature for both the streams. So, from there we can easily calculate the value of omega. Like for the first one, we can easily calculate omega S 1 should be equal to 0.622 into the saturation pressure corresponding to the wet bulb temperature for this one, divided by P minus P sat corresponding to this wet bulb temperature. Here everything is happening under standard atmospheric pressure. So, your P is equal to 101.325 kilopascal. If you are trying to plot this on a psychrometric chart, then you have to use a standard psychrometric chart corresponding to the standard atmospheric pressure. So, once we have omega is 1, you can just check this particular relation. From there we can get the final value of omega. So, putting this using the information about omega is 1 and the enthalpy values corresponding to the dry bulb and wet bulb temperature, you have the value of omega 1, which in this case will be coming as 0.0084 kg per kg of dry air, and accordingly enthalpy 1.005 into T dry bulb 1 plus 2500.9 plus 1.82 T dry bulb 1, this entire thing multiplied by omega 1, that putting the value of the dry bulb temperature, which is 15 in this case. Remember, here these temperatures are put in Celsius, that I keep on repeating because this is a deviation from whatever convention that we have followed so far. So, accordingly we are getting the value of enthalpy to be 36.85 kilojoule per kg of dry air. The same way you can calculate the specific volume as well. For the dry air part, we need to know the specific volume, because we have to calculate the mass flow rate also. So, specific volume for dry air corresponding to 1, how much it should be? So, it should be R bar, sorry, the gas constant for dry air part into T1 by P. Here T1 is put in Kelvin. So, for dry air we have to put the value of R, which is 0.287 into temperature 15 degree Celsius converted to Kelvin gives us 288 divided by 101.325. So, we get specific volume to be equal to 0.827 meter cube per kg. This is for the dry air part only. Accordingly, the mass flow rate for this dry air part becomes the total volume flow rate for the mixture divided by specific volume for the dry air part. Now, volume flow rate is 30 meter cube per minute divided by 0.827 meter cube per kg, which comes to be equal to 36.2 kg per minute. Just repeat the entire procedure for the second stream. For this case, your omega will be coming the following the similar procedure 0.01 kg per kg of dry air, H2 will be equal to 51.1 kilojoule per kg of dry air, and specific volume for the dry air part for this, which is again R dry air, but its temperature is T2, which is 25 degree Celsius, that is 298 Kelvin by pressure remains the same. So, this is coming as 0.859 meter cube per kg, from where we are getting the mass flow rate for the dry air part in the second stream, which is V2 by specific volume at this condition to be equal to 13.9 kg per minute. So, m dot dry air for the final stream is just addition of these two, because dry air part is directly getting added, and therefore, we are having 36.2 plus 13.9 to be equal to 50.1 kg per minute. So, from there you have to get the final dry bulb and wet bulb temperature. Using this mass flow rate, we can get omega 3. We know that omega 3 will be equal to m dot dry air 1 into omega 1 plus m dot dry air 2 into omega 2 by m dot dry air 3, which is coming to be equal to 0.0086 or 886 per kg of dry air, and H3, again H3 will be equal to m dot dry air 1 H1 plus m dot dry air 2 H2 divided by m dot dry air 3, which is coming as 40.8. So, we have to identify these 2 points. We can go for a mathematical analysis, or we can just straight away identify this point on the psychrometric chart to locate its this particular state point, and or you can go by the mathematical analysis, like as you already know omega 3 and H3. So, you can replace this H3 to be equal to 1.005 into T dry bulb corresponding to 3 plus omega 3 into 2500.9 plus 1.82 T dry bulb 3, from where you can get the value of T dry bulb at this point 3. I am giving you the final answer. The dry bulb temperature for the stream 3 is coming to be 17.5 degree Celsius, and the wet bulb temperature will be 14.5 degree Celsius. I have shown you how to get the dry bulb temperature. Try to find a way of estimating this wet bulb temperature, that I am leaving to you. Now, when this mixing process is happening, if I just quickly go back to the previous slide, here you can see here the final point 3 is located on the straight line joining point 2 and 1. So, suppose if you are dealing with a situation where one stream is extremely cold, whereas the other stream is hot and high in moisture content, like suppose your point 1 is located somewhere here and point 2 is located somewhere here. Then if you join them by a straight line, then it is very likely that point 3 is located somewhere outside the psychrometric chart. In that situation, of course, the additional moisture that is present in this situation is unfeasible, and therefore, the additional moisture that is present there, that will get condensed, just like the situation here. In certain situations, we get this mixing with the condensation process. It happens when we are mixing one very cold stream of air and another quite warm stream of air, which is also high in moisture content. Then depending upon the ratio of their mass flow rates, their final state may be located at this point 3, which is outside the psychrometric chart. And so, to have a feasible solution, it has to reject this additional amount of moisture, so that its moisture content comes back from omega 3, which is not feasible, to this omega 4, and accordingly the final state point will be omega 4, which will lie on this saturation curve. Correspondingly, there will be also a change in the temperature, because as this additional moisture which is present in the final mixture, that gets condensed, that will reject its latent heat, and by receiving that latent heat, there will be a rise in the temperature also. Like if we draw the projection, this is your T3 and this is your T4. So, this point is your T3, this point is your T4. Depending upon the location of T3 and T4 may have very small difference, like in these situations, or may have quite significant difference as well. Now, in order to identify the magnitude of this omega c, which refers to the volume of condenser, the mass of condensate that has been collected, that gets separated out. Then look at this point 4. So, what will be your omega c? Omega c is the difference between the specific humidity between 3 and 4. So, this is nothing but omega 3 minus omega 4, and therefore, omega 4 will be equal to omega 3 minus omega c. Now, from the previous analysis, we know that omega 3 can be written as m dot dry air 1 omega 1 plus m dot dry air 2 omega 2 by m dot dry air 1 plus m dot dry air 2, and minus we have the omega c. So, from measuring omega c, you can identify location of this point number 4 from here. Also, if we perform the energy balance to identify the temperature of this, then the final, let us say 1 and in the mixture, adiabatic mixture is receiving state 1 and 2, then at this point your state is 3, and then it is getting separated into 4 and omega c. Then if we perform an energy balance on this, then m dot dry air 3 H3 should be equal to m dot dry air 4 H4 plus omega c into Hf corresponding to the point 4, because it is most likely that actually it is difficult to say omega c will be at which temperature. Let us assume omega c to be at the temperature of 3 only, because it is getting formed because of the condensation of the moisture which is present at temperature T3. Then from there we have to identify H4. So, your H4 is becoming now m dot dry air 3 upon m dot dry air 4 into H3 plus omega c into Hf3 by m dot dry air 3. Now, m dot dry air 3 and m dot dry air 4 are same, because there is no change in the dry air quantity during this condensation process. So, it becomes just H3, these two cancels out, and we know that H3 can be written as m dot dry air 1 H1 plus m dot dry air 2 H2 by m dot dry air 1 m dot dry air 2. This is your H3, plus we have this here I have missed something. This is also multiplied by m dot dry air 4, because omega c is defined in terms of m dot dry air 4. So, we have m dot dry air 4. So, leaving us omega c into Hf3. As we have already calculated omega c from practical measurement or maybe from some other information, then you can easily look at the value of H4, and once you know H4, from H4 you can get the value of this T4 as well using the formula that we keep on using so till now. So, this mixing with condensation is not the most common process in air conditioning application, but in real life you must have seen this particular scenario. Like just think about an winter days, the situation scenario for an winter day where this stream 2 corresponds to the very cold air in contact with the ground, whereas the one may corresponds to the warm and moist air which may appear in the higher atmosphere during in the evening time or when the sun is out. When these two streams mix with each other, then what we see? We have seen the formation of fog or frost, which basically is the air containing lots of water molecules in the liquid form, in the form of very fine droplets. And this is nothing but this mixing with condensation, the mixing of very cold air in contact with the ground and more warmer air with high moisture content, they are mixing with together and leading to the formation of lots of minute water droplets which keeps on floating with the air. That is what we call the fog. Now, I would like to close this lecture by defining two factors which are very commonly used in standard air conditioning calculations. The first one is called the sensible heat factor. Before going to that factor, let us look at this diagram. Which process this one referring to, A to B or B to A? This is sensible heating or cooling process. So, during this process, how much is your total heat transfer? If Q dot S refers to the total heat transfer, then we can easily write this one as m dot dry air into H A minus H B, assuming it to be a cooling process, then H A will be okay. Let us write it as H B minus H A, assuming it to be a heating process. Q dot S is the amount of heat that has been added. This is purely a sensible heat transfer. Because the moisture contents remain the same, we know in this case omega B remains to be equal to omega A. There is no change in the moisture content, that is why it is purely sensible heat transfer, and that is why you are using this subscript Q dot S. The expression for this we can easily identify by putting the values for enthalpy. Okay, if we want to do that in this case, so m dot dry air for HB part, enthalpy can be written as 1.005 into T for point B plus 2500.9 plus 1.82 TB multiplied by omega at B minus 1.005 TA minus 2500.9 plus 1.82 TA into omega A. Now, omega B and omega A are equal to each other. So, in this case the 2500.9 that goes off, that leaves us 1.005 plus 1.82 into omega A, let us write, into TB minus TA. So, this way we can calculate the total amount of sensible heat transfer involved in this sensible heating or cooling process. Of course, TB minus TA, the symbol of that will depend upon the direction of the process. Now, what about this particular process? No change in temperature, but change in specific humidity. So, it is humidification or dehumidification process. B to C is the humidification, C to B is the dehumidification process. Here there is no change in temperature. So, we are having TB to be equal to TC. Then how much is the total heat transfer in this case? The total heat transfer involved in this case will be equal to the mass of dry air into Hc minus Hb, and this entire heat transfer actually is latent heat transfer, because there is no change in temperature, but only change in the moisture content. So, it is pure latent heat transfer, and that is why we are using the subscript L. How can we calculate the magnitude of this latent heat transfer? Here temperature is constant. So, m dot dry air into first for the Hc part 1.005 Tc plus 2500.9 plus 1.82 Tc into omega c minus 1.005 Tb 2500.9 plus 1.82 Tb into omega b. Now, in this case Tc and Tb are equal to each other while omega is changing. So, 1.005 into temperature, that cancels out, and accordingly we can write this one as m dot dry air into only the latent heat part 2500.9 plus 1.82, let us say Tb into omega c minus omega b. So, this is the corresponding latent heat transfer, the way we can calculate this for such kind of processes. Now, if we somehow combine these two processes, something like this, a heating and humidification or cooling and dehumidification process during which both temperature and specific humidity are changing. If we instead of visualizing the process from A to C or C to A, let us break this one into two ways. Let us consider an heating and humidification process A to C. So, let us visualize that the process initially happens from A to B as a sensible heat transfer and then from B to C as a latent heat transfer. Then how can we estimate the total heat transfer that can take place in this process? During this particular process, total sensible heat transfer, that is m dot dry air into Tb minus Ta, as we have seen in the previous case, Hb minus Ha, as we have seen in the previous case, whereas the latent heat transfer which is taking place during the second process, which is m dot dry air into Hc minus Hb. Of course, addition of this is giving you the total heat transfer Q dot T, let us say, which is Q dot S plus Q dot L by m dot dry air into the final enthalpy, which is Hc, minus the initial enthalpy Ha, and addition of the first two terms definitely is giving you the total heat transfer. Now, quite often here we define one particular parameter which is written as Q dot S, the sensible heat transfer, divided by the total heat transfer. That is, we have Hb minus Ha, the sensible heat transfer part, by Hc minus Ha, the total heat transfer. This particular factor is called the sensible heat factor, SHF. Similarly, the latent heat transfer part by the total heat transfer, that is Hc minus Hb by Hc minus Ha, that can be also written as 1 minus SHF. We do not need to define any other factor, because this is just 1 minus the sensible heat factor. The sensible heat factor is an important term in the designing of the air conditioning apparatus, because depending upon what kind of environment we are dealing with, the sensible heat transfer factor that keeps on varying, and accordingly you have to make modifications in the internal circuitry or arrangements of the internal cooling tubes. Common air conditioning applications are the domestic air conditioners. In normal climate, in normal dry climate, the sensible heat transfer fraction is quite high, latent heat fraction is quite low, and you may have sensible heat factor in the range of 0.75 to 0.8. Whereas, if you are dealing with a very humid climate, like outside the relative humidity may be in the range of 90% or something, or maybe it is raining, so it is very humid, then the sensible heat transfer may well go in the range of 0.6, which is quite low, which refers to extremely humid environment. And depending upon the sensible heat factor that is expected for your device, for your air conditioner, we have to design the system accordingly. Another design parameter that is also important, that is called the bypass factor. Just see the scenario that is shown here. Here we are starting from point 1 and we want to reach this temperature S. S refers to a point on the saturation curve. Now, to have this point, we of course have to provide a cooling surface. The moist air coming in contact with the cooling surface will lose its energy. Accordingly, there will be both cooling and dehumidification, and we may be having the final temperatures Ts. Now, let us say this is your cooling coil. Through the cooling coil, this cooling coil you can visualize as the evaporator of your refrigerant, of your refrigeration cycle. the refrigerant is flowing through the cooling coil, and accordingly the surface of this cooling coil is maintained at very low temperature. Now, the moist air is flowing over this. As the moist air is flowing over this, it is never possible that all the molecules of the air will be coming in contact with these cooling coils. Only a fraction of this total mass of air that you are supplying will be able to come in contact with the cooling coils, and accordingly they will be trying to approach this temperature S. So, this air is coming with temperature T1 and this coil is maintained at temperature Ts. Now, the portion of the air which comes in contact with the cooling coil, they will try to approach that temperature Ts, whereas the portion which is not coming in contact with this coil, they probably will be retaining its temperature T1, and therefore, the final temperature that we are going to get after the air passes through the cooling coil, that will not be equal to Ts, rather that will be equal to T2, this particular one, and this T2 can be visualized as a result of a mixing process between two streams. One stream which is the which has not come in contact with the cooling coil, continuing with temperature T1, other fraction which is coming in contact with the cooling coil has reduced to the temperature Ts. So, this T2 of course will be located somewhere along this straight line joining 1 and S, and the magnitude of this T2 or the position of this point 2 will definitely depend upon what fraction of air is coming in contact with this cooling surface. And to define that, we call this, we define this factor bypass factor denoted by X. Bypass factor refers to the fraction of air which has not come in contact with the cooling coil. This is the one, the portion which has not come in contact with the cooling surface, and there are several ways we can define the bypass factor. Like we can define it in terms of temperature directly. In that case, the bypass factor will be defined as T2 minus Ts by T1 minus Ts. T1 minus Ts is the maximum possible temperature change. Practically what happening is T1 minus T2. So, T2 minus Ts is a lost potential. That way you can visualize this bypass factor. We can also define this in terms of specific humidity, like the maximum possible change is omega 1 minus omega s, but practically we are having change only from omega 1 to omega 2. So, the lost portion is omega 2 minus omega s. Similarly, in terms of enthalpy also we can write it as H2 minus Hs by H1 minus Hs. Bypass factor can be defined following any of the three approaches, and because of the lack of information in practice, quite often we take all three of them to be equal to each other, and therefore, if the bypass factor is specified for a given air conditioner, then we can easily locate the point 2 from the knowledge of your evaporator temperature Ts. Similarly, 1 minus X, sometimes also called the contact factor, that refers to the fraction of air which has actually come in contact with the cooling coil. So, that is just the other part of that, which is T1 minus T2, the actual change in temperature that has taken place minus the maximum possible change. Similarly, in terms of omega, omega 1 minus omega 2 by omega 1 minus omega s. In terms of enthalpy, H1 minus H2 by H1 minus Hs. Both the specific heat factor and bypass factors are important design parameters. Similarly, there are several other design parameters also, but that is not required in the context of this course, because here we are more focused on the thermodynamic analysis. Any further progress or if I proceed from this particular point, that will enter real air conditioning calculations, but still I decided to mention about these two factors because they are very common for any kind of air conditioning devices. So, that this is the final diagram that we may have for a common summer air conditioning system. As the conditioned air goes to the room, it will pick up sensible heat and latent heat. So, it will pick up a total Qt amount of heat, then it is coming back at, let us say I refers to the indoor condition, then it is coming back with condition AI, and once it is while coming back, only a fraction of that is allowed to go out like this, remaining portion comes back and that gets mixed with this fresh conditioned air to have this state point 1, through which it enters your cooling and dehumidifying apertures, which is which you should visualize as the evaporator of your refrigeration system. Then 2 is the outlet condition, you may have a fan here to drive the flow, and with that it goes back to the room. This is a typical summer air conditioning system where we have the cooling and dehumidifying operation as the primary operation. Whereas, if you are talking about the winter air conditioning system, you may find that heating and humidification may be the most prominent mode of operation, but rest of the assembly may remain very much the same. So, that takes us to the end of module number 11, where we have talked about the properties of gas vapor mixtures. You are introduced to the concept of moist and dry air, specific and relative humidities, then different temperatures, dry bulb temperature, wet bulb temperature, dew point temperature. We have seen how we can combine these informations with the specific humidity to calculate enthalpy and specific volume of the mixture of moist air. Then the psychrometric chart was introduced, and you have seen how we can use the chart to identify the state points, or rather identify the properties corresponding to a given state point. We have seen different psychrometric processes both from mathematical point of view and also plotted them on the psychrometric chart. And finally, we are finishing with the definition of these two important factors, the sensible heat factor SHF and the bypass factor, often called the BF. So, that takes us to the end of module number 11. Air conditioning is an exhaustive area of research, and therefore, huge volume of literature, excellent books, very large books are available on this. So, if any of you are interested about this, you can easily go through any of the books of air conditioning. Several Indian authors and also overseas authors books are available, and please pick up any standard textbook to learn more about air conditioning if at all you are interested. But if your interest is only in applied thermodynamics, then this discussion should be sufficient. So, please solve the assignment problems, and if you have any query, write back to me. Thank you.